continue in the business of academia, and even if you don't, it's very important. So I'm from Madrid, but during my undergrad studies, I was in Texas for a year, beautiful year there. Then during my PhD studies, I went to Germany for the first time, but my own funding from the DAAD, which, by the way, has a specific programs with Brazil, so check those out because there's something specific. Then after graduation of my PhD, I went to Birmingham, so that was my first postdoc. After that, I returned to TU Dortmund, thanks to an award that I won in Germany and gave me the opportunity to do so. And then my boss over there moved to one of the Max Planck Institutes. It's the Max Planck Institute for Chemical Energy Conversion, sitting nearby. And I was there till 2020. And then the following year, the Nobel Prize in Chemistry was in that institute, Professor Benjamin List. So it's always kind of nice to say I was close to him. I was even in a party of one of the PhD students, a Christian advice, so it's always nice to say I was close to a Nobel laureate. And anyway, since 2020, July 2020, so now it's only 3 years since I am independent, right? With advantages and disadvantages, of course. You got to get the funding, but anyway. So the motivation of my work, why do I do this, or why do I want to study what I study, is because of the current role energy and chemical scenario, right? So petrochemicals are all over the place, but it dominates a lot of what we do, and it's rapidly becoming the largest driver of global demand, especially the chemical sector and the transport sector, which in the end relates to biofuels. So this is a little bit outdated. This is data until 2019, but you know what happened in 2020-21, so there may have been a little bit of decrease. But we can see here the ongoing growth of energy consumption, mainly driven by oil and gas and coal. And in parallel, there has been an ongoing growth of CO2 emissions. Yep. It needs to be recorded. I didn't get this. Sorry. Okay, I'll do my best. Apologies for that. Anyway, as I was saying, there's there has been an ongoing growth of CO2 emissions in accordance with the growth in energy consumption. So all over the world, in terms of fossil feedstocks and production of primary chemicals, this has been a huge demand and consumption. And in particular for Europe, a lot of these chemicals are hazardous either to the environment or human health, right? These are figures only for the European Union, but we can imagine that this is going on all over the world. So to mitigate that, especially the origin of all these chemicals, there has been a lot of legislation. Again, my focus is mostly Europe because I'm from there. I've been working in Spain, the UK, and Germany. But there has been a series of regulations spurring the use of renewable sources of energy, and then different bioeconomy strategies. This is the white paper in Germany. This is the one in Spain. This is the one in the UK. The UK came out of the European Union, but still these policies are normally still in place and ongoing. And obviously there's the big framework of the Sustainable Development Goals, to which my research contributes to affordable and clean energy or responsible consumption and production, amongst others. So the bottom line here is that there has to be a paradigm shift, and that there has to be a transition to bioeconomy and using renewable feedstock, and try to search for safer chemicals. So an overall view of my research, I like explaining this with this figure. It relates to what the introduction said, right? I like studying chemical reaction engineering, so I'm a guy that studies the use of catalysis and other reactions, try to model that. I study process intensification. For those of you who may not be familiar, probably you're not chemical engineers, so that is basically, or some of you may not be, it's basically a philosophy that advocates for the integration of processes or different unit operations in a single process unit. So think of doing a chemical reaction and then a separation. So instead of doing the reaction and then, for example, the distillation, you would do both in a single reactor, right? That's just one example. There's many others. And also the use of intensified mixing. A lot of you here, or some of you, use ultrasounds, for example, for your extractions. So that can be considered, or microwaves, that can be considered ways of process intensification, because it minimizes normally the energy inputs into the process, and that's very important. And then all of that following the principles of green chemistry. Again, for those of you who are not familiar, this is a set of 12 principles proposed by Professor Warner and Professor Anastas, and it advocates 12 principles relate to many things, but basically the summary of them all is that it advocates for a cleaner production of chemicals by selecting wisely operating conditions and solvents. So a summary of the things I'm going to cover today is here. I'm going to talk about points number 2 and number 3, reactions from liquid-liquid to liquid and liquid-liquid reactions. Maybe point number 4 I will skip, because I presume you're not chemical engineers, and that is more related to reactor design, and this may be a little too far out of the of what your interest might be, but I can cover something. In any case, the important thing here is that these are multi-phase environments, and what is key and what I do is more chemistry related rather than biomass related, even though I start from renewable chemicals. But the key thing is that you have to understand phase behavior in chemical reactions to then understand how to model that and be able to design chemical reactions afterwards for subsequent process design, simulation, techno-economic analysis, and so on, which is in the end what's going to constitute a chemical process. So let's start with the first example, and that is reactions going from a liquid-liquid, from 2 liquid phases, transforming into a liquid phase. And the substrate I've been using, and a lot of you are into, again, renewable chemicals, I've been using glycerol. So glycerol, as you know, is produced from biodiesel. So this is just a representation of the biodiesel cycle. But anyway, we know that biodiesel production takes place by the transesterification of triglycerides with an alcohol. All over the world is normally methanol, particularly in Brazil. Ethanol is, since you produce a lot of ethanol, normally that is what is used. And then the product is your alkyl ester, either ethyl or methyl ester, and glycerol. So the problem with glycerol is that it became, throughout the years, let's say an annoying commodity to deal with. It was a waste product whose price declined over the years. So that means that at some point, the companies even had to pay to get rid of it instead of getting value out of it. So when we know what happens when there's a mismatch between supply and demand, right? Prices decrease. So the point is to obtain value out of glycerol. How do we do that? There's different ways. You can burn it, but burn it in principle is not the wisest option. You can get energy out of that, of course, but so we can obtain value-added products by chemical reactions, different chemical reactions. You can do oxidations, you can do pyrolysis, you can do a lot of it. So my PhD thesis, and even though I continue these days with glycerol chemistry, I'm going to give an example of glycerol of what I did during my thesis, but it focused on the production of glycerol carbonate and solketal. And nowadays, I'm also studying some esters. So these products are used as fuel additives. They can be used also as green solvents and also in the formulation of healthcare products, particularly solketal. I've seen a lot of that in mouthwash, for example, and stuff like that. But there's other applications. So I'm going to cover only the example for the production of glycerol carbonate, because the reaction for solketal shows, even though it's different, it shows a similar phenomenology in terms of the transition from a liquid-liquid to a liquid phase. So let me show you this little video I prepared. So you can see that we have DMC, dimethyl carbonate, and glycerol at first, the 2 reactants of this reaction, and they are 2 phases. When mixing starts, we can see that it forms an emulsion, okay? So that is a biphasic system. Then we added, or I added, a basic catalyst, because this is a transesterification reaction and you require a basic catalyst. And as the products start generating, the interfacial tension between glycerol and dimethyl carbonate starts decreasing so much that there is a transition from your liquid-liquid system to a single liquid system. You saw what happened there, right? I mentioned interfacial tension. I don't know if you guys are familiar with what that means, but that's basically the amount of force per surface area that you have to apply to break an interface. So think that you have oil and water. If you have oil and water, they do not mix, right? If you use a cold solvent, eventually that interfacial tension will break, will decrease so much that there will be no longer two phases, okay? So that's what's going on. The thing is, I started my thesis in 2010. And until then, even though that reaction had been long reported, so I did not invent this reaction or anything like that, but everybody had been focusing on the development of catalysts, and that is great. I mean, people doing, making catalysts and then applying them, that's fantastic. But nobody had even reported in any of the papers this phenomenology. So for me, that was a big elephant in the room. Like it's obvious, why didn't nobody even acknowledge that? So what I did is I tried to model this system, to figure out how to find a mathematical equation to describe the progress of this reaction. So for that, I used an optical tool. This is called focus beam reflectance measurement. It's basically a probe that you put in a reactor, and there's a laser beam that's going to encounter the different droplets that are formed in that emulsion. Again, think of your oil and water. When you shake it, it forms little droplets, right? So what I did is follow the evolution of those droplets throughout time. So this is what this graph shows. This is the number of droplets that the FBRM, this optical technique, could count per unit time, per second in this case. And this is the progress of the reaction, right? This is the time on stream. So when I added a catalyst, in this case I added a different catalyst, but it's also basic catalyst. That's what you need again for transterifications. You can see that there is a decrease in the number of droplets until it reaches a point where there is 0 droplets. So what happens when there's 0 droplets? That's the point when there's no longer 2 phases, but only 1. Therefore, the transition from liquid-liquid to liquid, okay? So I was able to synthetically, let's put it this way, relate the composition. Well, basically, on top of doing the analysis, I also analyzed by HPLC, right, chromatography, the progress of the reaction. And it gave me a conversion of around 30% of glycerol, okay? Starting the reaction, this transition from 2 phases to 1 phase occurred when there was a conversion of 30%. That corresponds to a composition of my reaction system consisting of the 4 components. And this is what I tried to represent here in this ternary diagram. Ternary diagrams normally are meant to represent 3 compounds, but in this case what I did is my polar phase, glycerol, the composition of my non-polar phase, dimethyl carbonate, and then I artificially joined together the composition of the 2 products. In this way, I was able to determine the liquid-liquid equilibria. This curve that you see here is what separates the composition of a system between having 2 liquid phases and 1 liquid phase. So what this means is basically if you have a composition of, for example here, I don't know if you know how to read these diagrams. They are a little tricky sometimes if you're not, if you haven't studied liquid-liquid extraction. But anyway, what this means is if you have a composition in this point here, you have a biphasic system. But if you have it, for example, here, it's a single phase. And what I was able to do is relate these observations that I did with the laser to the composition of the system. If you see these points are falling at that curve that separates the monophasic from the biphasic system, and that is precisely the compositions at which there is no longer droplets, okay? So then with all these observations, as a chemical engineer, we like modeling a little bit. I'm not a great modeler, but I like doing a little bit of this, and it's important for reactor design afterwards. This is very long, so I'm just gonna say that I was able to derive a model that took into account that transition that I observed, okay? Then this is basically how the system behaves over time. These are the experimental points, right? What you see here. and the line represents the model. And thankfully, after many trials, believe me, it didn't come out easy, but I saw that the model fit well. And this is what can be seen in this parity plot. What this diagram, what this graph represents is the similarity between the predicted value of my model and the actual experimental value. So if everything falls around this diagonal line, it means that the model was able to predict well. I did the same for another reaction, basically same story, me trying models, but same thing. On top of this, I realized that sometimes you can use certain conditions to your advantage. So remember that I started with a biphasic system, right? The glycerol and another reactant. So in this case, I started with glycerol and propylene carbonate. It's a similar compound to the ones I described before, but this shows the peculiarity that if you increase temperature, you can enhance the miscibility of them. And that is what it's called a thermoresponsive behavior. There's other types of response behavior, sometimes pH responsive behavior, CO2 responsive behaviors, and that's going to allow a change of the physical properties, in this case solubility, mutual solubility of the compounds, to use that to your advantage. So why would it be advantage to apply temperature to then have these two compounds soluble? The advantage is that when we have multi-phase systems, there's always something called mass transfer limitations. So the rate at which the process occurs, or the reaction occurs, is not just the rate at which the chemical reaction occurs, but you also have to take into account mass transfer limitations. Think about when you have a liquid and a solid. The larger the solid, the bigger the solid, the longer it takes for the liquid to diffuse inside. You may have noticed this when you, I don't know, when you're preparing your biomass and you're breaking the biomass and then you have to sieve it. The smaller the biomass, normally your extraction process, if you're doing, for example, supercritical extraction, CO2 extraction, or whatever you're doing, it will take faster when the biomass is smaller. Then there's disadvantages to that, like pressure loss and all these kind of things. But the point is, when there's an interface, reactions or extractions, processes in general, take place more slowly. So by using temperature, I was able to operate in a single liquid phase, and therefore the reaction went faster. Then again, what this graph means is that I was able to determine the liquid-liquid equilibrium between these two compounds, glycerol and propylene carbonate. And I identified a series of a composition and a temperature at which I was able to operate like that. Then a little bit of modeling again. I don't need to go through that again. But anyway, the point is, use physical properties to your advantage to operate without mass transfer limitations. That's the overall message here. This is Aya. This is my student, one of my PhD students. So one of the things I've been doing, so what I showed you before was basically what I like calling the sigma Aldrich experiments, right? I was operating with 99.9% pure glycerol. Life is beautiful. You don't have any other complications, but they are necessary studies to understand, the basic phenomenology. But with Aya, I'm trying something different. First, I'm changing the reaction. So she's doing glycerol esterification with acetic acid, and the product to be obtained is triacetin, which is also a biofuel additive, and it's quite well valued. Okay? So the approach here, the problem, this reaction offers one problem. In this case, it's not a liquid-liquid phase reaction, so nothing like that. But the problem is the following. This is 3 in-series reactions that are in equilibrium. If you remember from probably your basic chemistry in first or second year of your degrees, you may remember Le Chatelier's principle, right? Like, if you want an equilibrium reaction to proceed to the products, either you can increase the molar ratio of the reactants, right? Like well, you can also change it with thermodynamics, temperature, and so on. But you can either add more of one of the reactants or remove one of the products. This is water. This is very small. So the strategy here we want to follow is to remove water in situ. So by doing that, then we will push the reaction towards the products. But then the other complication is that we want to use the nasty stuff. So not our Sigma Aldrich glycerol, but we want to use real glycerol from a supplier, from a biodiesel producer. So this is what they get out of the process. It looks disgusting. There's a lot of stuff going on there, the catalyst, a lot of salts, you know. So we, or Aya rather, is doing a purification of that glycerol to get it to a composition, let's say a decent purity, so we can operate and operate in, let's say, more normal conditions, right? So far she's been making efforts. She's achieved 74% purity. We can achieve higher, but the point, what we want to do is apply a catalyst and then derive a kinetic model. And that kinetic model, considering that the composition is going to have some ashes, perhaps, and some other impurities, we want to derive a model that takes into account those impurities. Anyway, this is ongoing work. This is just her starting a few months ago, so that is that. So that's the end of the story for the liquid-liquid to liquid reactions. And I'm going to go into liquid-liquid reactions, like stains throughout as a liquid-liquid system. So why do we use multi-phase systems, right? The story I told before is because of the nature of the reactants. That's that. We cannot help it. But here, what we want to use is a biophysical strategy to intensify the reaction. That is to perform ways to separate products from catalysts and then be able to recycle everything, okay? So there's different approaches to do this. The advantage of doing this, if we're using a homogeneous catalyst, if we're using a heterogeneous catalyst, it's easy, you can filter it out, you know, a solid, that's easy. But when you're using a catalyst in solution, recycling a homogeneous catalyst is hard. So we use strategies whereby we use interfaces to recycle that. So one opportunity is to do a reaction and separation. This is in German, sorry. I took it from a German book, but anyway, the point is we can have a reaction phase where the catalyst, this is the K for catalyst, is present, and then our substrate is transformed into a product, and then the product has a different polarity than the substrate and will separate into a second liquid phase, right? If you change the polarity of the product, then it will not be miscible anymore, okay? So that is one approach. One example of this is it's a commercial process established by Shell, and this is to produce olefins from ethylene, okay? So the idea is you have your polar phase in which your catalyst is present. In this case, it's a nickel-based catalyst. You pump or infuse, rather, ethylene as a gas in there, and then as it reacts, this is an olefin whose polarity is way different to that of water. Therefore, it's going to separate into another liquid phase, right? So the idea is change the polarity to then separate and continue using the phase in which the catalyst is present. Another option is to do a chemical reaction where the substrate goes to the product and then separate the product by extraction afterwards and then separate your solvent. This is not really process intensification, right? Because this is using two different units to do reaction and separation. This has been also reported for another process, telomerization of butadiene. This is to produce surfactants. It's a quite old school process. But anyway, the point is that you need to recycle your palladium catalyst because palladium is also quite expensive. But the idea to do this is to do reaction with in situ extraction. So merge that reaction and liquid-liquid extraction into a single unit. In this way, what we can do is our product, our substrate reacts in a phase that contains the catalyst, and then it's extracted into a second liquid phase. Then obviously we're going to have to recycle that phase by using distillation, for example. But it has many advantages. The reasons why we want to separate products in situ is, for example, we can avoid undesired side reactions. So if our product reacts farther, we want to take it away, because otherwise if it continues to react, then we don't get the product that we actually want. I'll give an example, a specific example later, because that's what I'm working on. Another example is, and linking back to Aya's project, is if we have a reaction that is thermodynamically limited, we can extract, we can take the product away and then push an equilibrium reaction to the products. And another example would be, I was talking to Professor Adriano Mariano yesterday, and for some of his fermentations, for example, he had inhibition by product. So he was doing fermentations to produce butanol, and he has to remove the butanol because eventually that will kill his bacteria. So he's not using a liquid-liquid approach, he's doing something else. But the point is, if you extract that product, you can avoid killing your bacteria, or if you're using enzymatic reactions, you can avoid inhibition by product. So that is something that may be relevant in some of your cases. So if you ever have a problem where your product is killing your catalyst, whether it is biocatalyst or enzyme, you may think, oh, I need to get rid of this product. How do I do it? Whilst the reaction is taking place. Yeah, this is what happens in another reaction. I'm just going to skip this and jump to the specific example why I use liquid-liquid phase systems, okay? And that relates again to biomass, so I'm going back to your world. So the idea is, well, from biomass, from lignocellulosic biomass, we can fractionate that and obtain lignin. I'm not going to talk about that. Lignin chemistry is very hard, and it's a world that I don't want to get into yet, maybe in the future. But then you can also obtain the hemicellulose and cellulose platforms that by hydrolysis can lead to single sugars like xylose and glucose that can be isomerized into fructose, okay? I'm going to focus only on the use of these sugars to produce, by dehydration, furfural from xylose, or HMF from dehydration of fructose, or else, like I said, isomerization plus dehydration of glucose. Then from these products, well, rather than products, I like calling them building blocks. From these building blocks, you can obtain many other products by different chemical reactions. I'm not going to go into those because, like I said, I want to focus on this. In any case, all of these products are also used as fuel additives, as solvents, monomers to bioplastics. For example, FDCA, that's the oxidation product of HMF. This is, at least in Europe, probably here as well, but it's very well regarded as one of the monomers to obtain PEF, polyethylene furoate, which is meant to be a substitute for PET. So it's a quite interesting chemical. Anyway, that reaction, the dehydration reaction of the sugars to furfural or HMF, traditionally it's been taking place in a single liquid phase, normally aqueous, because you need to dissolve your sugar, and in the presence of an acidic catalyst. The problem is the following, and linking back to what I explained before. These products may undergo undesired side reactions. So HMF, in the presence of water, may rehydrate to levulinic acid and formic acid. So those are good products. There's nothing wrong with them, but it's not what we want, right? Like, we want to get HMF. And on top of that, both HMF and furfural may react with themselves. It's called a self-condensation reaction to produce something called humans. Humans is basically a nasty polymer that comes up, and if you're doing your reaction, you'll see small black particles appearing there. So again, we don't want that. So the strategy is to use an organic phase to perform the in situ extraction of HMF and furfural, and hence mitigate the progress of these nasty reactions that we don't want to happen. And this aligns with, again, with the vision of process intensification, doing two operations at the same time, that kind of thing. Question is, what organic solvent do we use? In principle, we could go to the lab. We could spend a ton of time working, testing by trial and error, and we could spend a lot of money. And I know here some researchers have been telling me that ordering chemicals can become a little bit of a nightmare sometimes. Like, you have to do it well in advance because it takes a while for chemicals to arrive. So even more to the point. So I followed two criteria to try and select my solvents. The first of them, even though it's not the most important, is to try and go as green as possible. So since we are using renewable chemicals and there's this transition to, we want to operate as cleanly as possible. So I want to select solvents that have a favorable environmental, health, and safety performance. For that, there's very good guides in literature. I personally recommend this Chem 21 guide. This was published, I don't know if it's maybe too small, but I can send a reference later if you want. This was published in the Journal of Green Chemistry in 2016, and it provides also an Excel spreadsheet that you can use to determine whether the solvent you are considering has a green profile or not, for simplification. But most importantly, on top of the solvent being green, it has to do the job. I mean, if it doesn't do the job, then it doesn't matter how green it is, right? So again, instead of just going to the lab, trial and error, try 1,000 solvents, waste a lot of time, we may want to use predictive methodologies. So the one, there's several ones, but the one I focused on is based on quantum chemical computational predictions, and it's called the COSMO-RS method. For those of you who are not familiar, I don't know if anybody, well, I know Felipe definitely is familiar with that. He was doing that with me in Manchester. But for those of you who are not familiar, it basically consists of two steps, right? The first one, and that's not really the COSMO-RS method, but it's a necessary condition. You have to optimize the geometry of your molecule, right? So optimize the charge density around the surface of your molecule, because that's the information that the COSMO-RS method is going to use. So you do that with DFT calculations. You can use software like Gaussian or TurboMol, but basically it's molecular optimization for simplification. I'm no expert in DFT, but to simplify it a lot is basically simulate and optimize the geometry of your molecule and the charge density around that. And that information is reflected in the so-called sigma profile. You can consider this a histogram of the probability of the density of charge around different positions of the molecule. Okay? I don't know if that's too abstract, but more or less that's what it is. With this information, the COSMO-RS method, biostatistical thermodynamics, can compute chemical potentials. And that information with chemical potentials, that chemical potential can be related to properties like solubility or fluid phase equilibria, vapor-liquid or liquid-liquid equilibria. And that's exactly what I wanted to do, right? Like if I'm gonna do an extraction, I want to predict the liquid-liquid equilibria. That is how my compound, my solute, in this case either HMF or furfural, is going to partition between the two liquid phases, right? So this is the methodology I used. I started selecting solvents. I mean, you have a massive database of 3,000, 4,000 compounds. If I already know I want to use the green chemicals, or at least typically use chemicals in industry, I always start narrowing down my list. You don't have to necessarily, but I do it for practical reasons. And then you have to check that your liquids, right, that your water in this case, and your organic solvent are immiscible, because if they mix, then there's no liquid extraction, of course. And then basically, through a series of steps, to summarize, what I do is compute the liquid-liquid equilibrium that's going to let me calculate a partition coefficient. So the partition coefficient is defined as how much of my solute, in this case, again, HMF or furfural, goes into my organic phase with respect with how much of it goes to the aqueous phase. So if we want to extract, what we want is a partition coefficient as high as possible, right? If we want it to be in the organic phase, the higher that value is, the more favorable the extraction is, right? So this is basically, yeah, unfortunately this is too small, but this is a diagram that reflects the top 10 or 11 candidates. I always like using some reference compounds, that's why there's 11 instead of 10. But basically what this shows is that ethyl acetate and methyl propionate have the highest partition coefficients for furfural and HMF, on top of having a good environmental, remember the EHS parameters for green chemistry, environmental, health and safety, So a good environmental score, a health score, and safety score, right? So the best two, like I said, were methylpropionate and ethyl acetate. So those are esters. And they are great solvents and everything, and you can do the extraction with them. However, if you remember what I was telling before about the chemical reaction, this reaction requires an acid catalyst. And what happens to esters in the presence of an acid catalyst is that they hydrolyze. So you obtain the corresponding organic acid and the corresponding alcohol. So they are no longer really solvents, but they are reactants, and we don't want that in our reaction. Therefore, we dismiss this from our application for our particular reaction within situ application. And instead, we want to use methyl isobutyl ketone, which is also green solvent, and it's inert under these reaction conditions. So that's what you expect from a separation agent. So yeah, I'm very proud of this work. I like spending a little bit of time on that because I was fortunate enough with all this screening and all this reasoning and all that, we were able to make it to the cover of the journal Green Chemistry. So that's always I'm very proud of. And on top of that, it gave me a prize for postdoctoral researchers when I was still at the Max Planck Society, and gave me a little bit of funding to continue collaboration with my former supervisor in Germany. So I have very good memories of that work. But on top of selecting the solvent, I'm a chemical reaction guy, so now I want to study the chemical reaction. So remember when I said before that you have to look for ways and try and find a stimulus, in this case, temperature, to your advantage? So here, by default, because we want to do a reaction with an in situ extraction, we're always going to have two liquid phases. But then, for the catalyst, I wanted something that would behave as a solid at room temperature, but then I wanted to prevent mass transfer limitations while operating at reaction temperatures. So what I did is I found, the concept is use something, an acid catalyst that's going to be solid at room temperature, then increase temperature, operate as if there was no such solid, and then again, when you cool down after the reaction, you precipitate. So in a way, it's as if we were providing with an invisibility cloak to our catalyst in terms of solid liquid mass transfer limitations, right? Internal diffusion, right? So then I tried different catalysts. I checked solubilities. I checked, okay, I said, my thinking was, let's find something that is not soluble in water at room temperature, but then if I increase the temperature, it becomes soluble. I identified a few: phthalate acid, isophthalic acid. Since I tried those two, obviously I tried terephthalic acid, right, like to continue the trend. I tried orthotoluic acid and EDTA. And this graph here is basically what the recyclability of that solid upon dissolution happened throughout several cycles. So I saw that EDTA was very highly recoverable. After 5 cycles, I lost something like 6% of the mass. Could be better, but it's to prove the concept, I think it was enough. Obviously, if you go to the industry and you lose 6% in 5 cycles, they may not be super happy about that. But anyway, the concept is, again, try and make use of the properties, right? So I used EDTA. And then I had these biphasic systems. And again, I'm a modeling guy and a kinetic modeling guy. So then this is the reaction to obtain HMF. This is the reaction to obtain furfural. This is slightly more complex because of the side reactions that I mentioned before. These are the ones that we don't want. And in the case of furfural, it's a little more simple. But the point is, and again, linking back to mass transfer limitations, when there's extraction and you want to model the kinetics of the reaction, you have to focus on the reaction. So we have to operate under conditions in which we don't have those mass transfer limitations. So how do we determine this in liquid-liquid systems? What we do is we scan different stirring rates. So if we prove that operating at different stirring rates, we get a similar performance of the reaction, that means that liquid-liquid mass transfer, liquid-liquid diffusion, well, diffusion is more for solids, liquid-liquid mass transfer does not really play a role in the kinetics. And therefore, we can be sure that the equations we propose correspond to purely kinetic reactions, like the classic rate equations. You may remember this again from maybe not basic chemistry, but if you didn't do chemical engineering, probably you didn't see this. But if you have, these are classic equations to model the kinetics. Okay, I'm not going to go a lot into that, but what I want to say is make sure you are not measuring other phenomena. That's the important thing here, regardless of whether you're studying chemical reaction or not. Like if you want to study one phenomenon, whether it's separation, reaction, or something else, what you want to do is isolate phenomena so that you can say, okay, this is what I'm studying. And to isolate phenomena, you may have to use extreme conditions, whether it is by putting a very small particle size or very high stirring, you know, that kind of thing. Anyway, yeah, this is me saying again that the model more or less fits well to the data. Again, the line represents the model and the points are the experimental data. Here the quality is not great, so we might have to repeat those experiments, but anyway. And this again links to another project I'm doing, but it's very similar. The idea behind Dominic's project is to extract CMF. CMF is similar to HMF and furfural, but it offers other opportunities in terms of synthesis. So more downstream processing, you know, like people operating with that as a building block. And then the idea, on top of using COSMOS, was to use also Hansen solubility parameters, which is another strategy to determine the solubility of compounds into solvents. With that, we're collaborating with Felipe over there. So it's ongoing work, but it will come out hopefully soon enough. And obviously, one thing is the models. Also, guys, if you ever do anything with models, with predictive models, it's very important that you validate experiments, okay? There's a tendency to believe blindly what a model says, and it's not necessarily true. So please validate everything. Go to the lab and say, okay, is this prediction true or not? You know, because not always it's true. Models are good, but they are models. It's not reality, okay? And again, all those experiments were the Sigma Aldrich experiments, so me using the pure sugars, right, to study this phenomenology. But now my ambition is to jump. This is a proposal. This is a figure that summarizes a proposal that I submitted for UK Research and Innovation, public agency there. And I basically want to use potato peel waste. So potatoes are, I mean, the agricultural industry in the UK is nothing compared to Brazil, but it's one of the main residues generated from that activity. And it offers the advantage that you can separate bioactive compounds, talking about flavonoids, talking about phenolic compounds. So the idea is to do first solid liquid extraction using possibly novel solvents, but in order to evaluate that extraction and prevent me going to the lab and using 1,000 solvents, I want to use this COSMOS methodology. And then after I extract these phenolics and flavonoids, the idea is to use the remaining biomass with a high carbohydrate content to obtain the furans that I was talking about, right? HMF, furfural, and CMF, chloromethyl furfural. This is, let's see, by the end of the month, I should know if I get the funding or not. If I don't get the funding, I will have to put this on hold. I mean, we know how it goes, right? And this is for gas liquid reactions. I don't think I'm going to go into that because this is more about reactor design, and probably that's too much out of the realm of this faculty. But anyway, going back to my vision for research, the idea is to start with predictions, then go to lab scale and validate, test which solvents in small scale could be good for these separations, and so on. Then go up to a reactor scale, probably about half a liter, 400 mils, in which I can do these kinetic experiments to obtain these equations I was talking about, right? And then design advanced reactors for implementation in higher technology readiness levels. I am not at this point yet, except for a few things I did when I was back in Germany. But me being in a new place, obviously, it takes a while until you can scale things up. So in conclusion, development of bioeconomy and biorefineries is something that's happening, and it's being explored by law. There's, I'm not going to say a lot because it's never a lot, but there's a little bit more funding for this kind of activities. In England, for example, in the UK, they give a lot of importance to the net zero strategy, and in Europe as well. I don't know about here, but I presume they want to some extent to move in that direction. Multi-phase systems can occur either because reactants are like that, or because we can use engineering strategies to prevent side reactions and this kind of thing. And that means that we can use solvents or chemicals that don't like each other to apply them in a favorable way, right? Appropriate selection of solvents. You don't want to go to the lab. You don't want to spend a lot of time. You want to go do as little effort as possible and go as green as possible. And again, and I gave a lot of emphasis to this because over the years I've worked a lot with chemists, and chemists are brilliant at understanding reaction mechanisms, synthesizing catalysts. I don't know how to do that. But normally they don't realize that they may be, when they evaluate the reaction performance, they may be evaluating two phenomena at the same time. And that's dangerous because then you're not really measuring how good your catalyst is, but you're measuring how good your catalyst is with whether mass transfers occur or not. So it's important to understand how to operate, to observe what you want to observe. And yeah, that's that. So I just want to, well, these are some of the awards I got over the years because I covered a little bit of what I did. I've been fortunate enough to be regarded. I'm very proud particularly of the Green Talents Award, and it's something I'm also a little bit of an ambassador to the program. So if your research fits into the biomass utilization and that kind of thing, you may want to check out this program. It's a program by the German government. It offers a great opportunity to spend 2 weeks there, meet with collaborators there, and then the following year come back on a 3-month research stay at a place of your choice, in Germany, of course. These are my supervisors over the years when I was still not independent. So at the Complutense University, University of Birmingham, Dortmund, and Max Planck. Andreas particularly helped me a lot in my career, so I always like mentioning him a lot. And of course, my PhD supervisors in Madrid. And that is that, acknowledging my group, the funding by FAPESP. That's why I'm here today, with collaboration with Professor Cristiano Soledad Funari at UNESP. And this is my group. I have other 2 students. One of them is starting in September. The other one is in another place. But anyway, this is us. This is not Manchester. This is Belfast. We went to a conference together. But anyway, these are Aya and Dominic. And if you're ever interested in for a postdoc or something, contact me. There's different opportunities. Thankfully, I know that FAPESP also offers possibilities to move. So I'm happy to talk. Manchester is a great place. We do great science. We are very high up in the rankings. This year we are the 15th in chemical engineering, and we were the first in the Times Higher Education Impact Rankings. So we do great stuff, and that is the city of Manchester. I don't like this team, but they're the European champions. So whatever, I have to deal with that. I'm more of a Man U fan, and then if you're into the music world, I mean, this is a place where a lot of the music scene, so it's important to do science, but from time to time, if you have a chance to have fun, that's always great. So that was that. Thanks for listening, and if you want to talk or have any questions, I'm happy to take them. Thank you.
Thank you, Dr. Esteban. Nice presentation. In food engineer graduation, I give classes about liquid extraction. Very nice, interesting. And now we're going to open the questions.
I hope it wasn't too long.
Oh, which is great.
All right.
Thank you very much for your presentation. Very interesting. Give me several ideas that I would like to discuss with you later.
Of course.
But my first question regards ultrasounds. I love ultrasounds. I've been working with it for several decades. It was part of my PhD thesis, you know, and listening to your comments regarding temperature made a lot of sense exploring ultrasounds to not only enhance the reaction rate, but also to increase temperature. Have you considered using temperature ultrasound as a temperature source?
Yes. I got last year. I got some pump priming, some internal funds of the university. I got a nice piece. I was discussing that precisely with Monique and Felipe before. For homogenization for this liquid-liquid interfaces is crucial. My student right now is not focusing on that, but I'm gonna force him to, because also I paid for that equipment. I want to use it. But yes, definitely that's one direction to go, because then you can. What I want to do specifically is compare the energy input with ultrasound and the energy input with regular mechanical stirring. I want to do that because then that also gives like a little bit. When you publish that, of course, you know, it gives like a good view of process intensification. You know, all this idea of minimizing energy inputs and that thing. So yes, I'm going to use it for liquid-liquid systems, and I'm going to use it for solid-liquid extraction. If I get the potato project, I wanna do it with that. Yep.
Very interesting. I'm also very interested in reactor design, and I was wondering, because the reaction time you showed was relatively long reaction times. Do you think it's carried out on static reactors, as I understand, just stirring them on a vessel, mixing them? Do you think it's possible to implement such as liquid-liquid separation in dynamic systems, such as a semi-continuous flow through reactor?
So that's one of the ideas. The part I skipped at the very last because I thought maybe it was not going to be so relevant is I want to do, again, I need the funds, I need to scale things up, and before scaling things up, I want to go small and understand, you know, all that. But one of the ideas I have, again, related to process intensification is the use of a static mixer. So static mixers, for those of you who don't know, are basically tubular reactors with a lot of elements inside, for lack of a better word, that promote droplets and bubble if you use gases, if not droplet breakage. And that the only thing you have to do is pump it through. I mean, pumping, of course, it's not for free, but either way, if you have a continuous process, you're gonna have to pump. So the idea is to use this flow-through reactor, this is a static mixer, and then the separation would come at a tank at the end of that pipe, more or less. So yeah, that's also an idea, but that's not for now. That's more when I want to go continuous. First, I'm still doing batch.
Thank you very much. Later, I will discuss some ideas with you, and maybe
yes,
we can
please.
have more ideas.
Yes, happy to hear them.
Thank you.
Good.
More questions?
Thank you for the presentation. You can explain again, please, the production of furfural? Because I understand this agitation is the more operational parent, is more important. You can explain?
So furfural it happens by the dehydration of xylose, or a C5 sugar, but normally you would start with xylose. Then, as far as I've observed from the kinetics, it requires higher temperatures, meaning it has a higher activation energy for the reaction to take place. Then agitation specifically, I haven't seen that to play a role, neither for the reaction or for the liquid-liquid extraction, at least at the stirring rates that I tested. So I showed a graph where there was like 200 revolutions per minute and above. I mean, speaking of revolutions per minute doesn't make sense. You really have to talk about the Sherwood numbers and all the energy inputs. But anyway, the point is, agitation doesn't really play a role. Temperature definitely does. But at the same time, you got to be careful not to promote too much the the self-condensation to humans. So yeah, so I think temperature is the major player here, not agitation.
Okay. And you use extraction temperatures or hydrolysis temperatures?
I use, so for I use under temperatures at which hydrolysis take place. So that is normally 170, 160 degrees. That's how I operate with that.
Okay, thank you.
All right.
Thank you.
More questions?
Thanks for your presentation.
Thank you.
I guess most of the people in this room, at least this side here, they work with or they're interested in processes in which they want to convert xylose and glucose into bioproducts using microbes, for example.
Yep.
And whenever you have to pre-treat your biomass to get xylose and glucose, you have side reactions leading to HMF and furfural, which is the stuff you are interested in.
Right.
So I was just thinking, does it make sense to think about combining the two things? Like,
Problem is, if I am not mistaken, that HMF and furfural can, you guys may correct me in this, I'm not 100% sure, but I think they can be inhibitors of microbial activity.
yes, so
Doing the extraction,
people want to get rid of them, and you want them as a substrate. That's
Right.
what I'm thinking here.
so doing this with an extraction could help. The problem is, when you do the hydrolysis of your biomass, how do you do it? Enzymatic, I guess? Is it with enzymes, or how do you guys do it? That it might make it could make sense to then extract those compounds. What I don't know is, or what something to make sure of, is that the solvents that you test are not inhibitors of either those enzymes if you're using enzymatic hydrolysis. But for the high pressure treatment, it shouldn't kill anything because there's no enzyme or bacteria in there. So maybe it's an option. It could be an option.
Because the pre-treatment to use high temperature, high pressure, and they produce inhibitors to microorganisms, furfural and methylfurfural, and very nice to optimize the process to extraction for these compounds, because for the fermentations is not good.
Yeah, yeah. Using this biophysical approach could help. The same way like I said before with Adriano yesterday, I was thinking, like, I mean, he's getting rid of butanol in a different way, but butanol was killing his bacteria, so get rid of butanol. And I've seen that in literature, some people using solvent, I don't remember specifically which, but using solvents to get rid of butanol, not to kill the bacteria. So I think it could be a way using a biphasic system. Then if you're using if you're not using enzymes or anything, I think it could work. If you're using enzymes, then you gotta be careful that the solvent doesn't kill your enzyme, or doesn't deactivate your enzyme, but it could be something, definitely, yes. Well, I'm happy it led to an idea. Maybe you tried and it doesn't work, but at least there's something new to try, I guess. So that's the point of doing this.
More questions?
All right.
Okay, thank you so much.
Thank you very much. Thanks for the questions too. Yeah. Thanks very much. It was nice. I hope it wasn't too long.
No, that's okay. Enjoy Campinas, enjoy Brazil.
Yeah. Unfortunately, I'm going back tomorrow, but today I'm traveling to Sao Paulo, and hopefully I'll have a few hours to see the city. I know it's massive. I'm not going to see even 5% of the city, but anyway.
You